All right, let's talk about air resistance and terminal velocity. So, free fall. First, we need to talk about free fall. This is a situation where gravity is the only force that is acting on an object. In these free fall scenarios, you're going to assume that there is no air resistance acting on the object. So you could have a person falling, and the only force acting on it is gravity. And remember, gravity pulls us down at 9.8 meters per second squared. That means for every second that the object falls, it gains speed by 9.8. So let's keep going. Another concept is air resistance. So we've already talked about air resistance. It's a force that we've been drawing on our free body diagrams. And it's the force the air applies on a moving object. It attempts to slow down falling objects, so it's similar to friction. So here we have two parachuters, one that is 100 kilograms, one that is 150 kilograms. So if you can compare the two people that are jumping through the air with a parachute, you'll notice that the more mass that the person has, the larger the magnitudes of the gravity and the air resistance. So notice that the magnitude for the 150 kilogram guy is way larger than the magnitude for the 100 kilogram dude. All right, so we're going to be talking about objects that are falling, right? So if a body is released from rest, it starts to have gravity acting on it. So remember, we can write this as Fw for weight, or we can write it as Fg for gravity. Weight's calculated by mass times gravity. So any of that's fine. So as the body is released and it falls through the air, usually air resistance is acting on the object. So, to draw the forces acting on the object, you still have gravity downward, and then you have drag force going upward. Drag force, air resistance force, either of those is fine. So as it continues to fall, you'll notice that this drag force gets larger. And eventually, the drag force is going to be equal to this gravity force. So these arrows are the exact same length. So when these forces are the exact same length, the body is at terminal velocity. So terminal velocity is the maximum speed a falling object reaches when dropped from rest. So maybe at first the object is at rest, so has a speed of 0 meters per second. As it's falling, it goes from 0 to maybe 5, 10, 15, 16, and then maybe it ends up going 16 meters per second for the entire rest of its journey down. So an object reaches terminal velocity when the force of gravity is balanced or equal to the force of air resistance. So let's look at another scenario. So we have a person who has a mass of 90 kilograms. And remember, to find the weight of a person, we're going to do mass times gravity. So when you do 90 times 9.8, you're going to get 882. So we have a weight vector on each of these parachuters, or people jumping out of the air, falling through the sky. Not really sure what's going on. It looks like their parachute is not deployed. But you'll notice that the gravity force acting on the person is the same. 882 newtons down, or negative. Negative sign because it's a downward vector. All right, so in the beginning, the object is dropped, and the force of gravity, Fg, Fw, is much greater than the force of air resistance. So you'll see that the vectors are uneven. The force of weight, or gravity, is 882 down, and then the drag force is 0. It's 0, so no drag yet. So the force of air resistance, so Fa or Fd as shown in this diagram, Fd for drag, increases as the speed of the falling object increases. So what that means is these two middle diagrams, this is the person still falling. So you'll notice that the drag goes from 0 to 300 to 600. So the air resistance, or the drag, is increasing as the person is falling. So that's because this gravity is acting on the object, pulling it towards the center of the earth, right? So remember, everything as it falls, it accelerates due to gravity. So essentially at the beginning, there was an acceleration of 9.8 meters per second squared, and that's because there was no drag to interfere with the gravity. As we start adding drag, so now there's air resistance of 300 newtons, now the acceleration is slightly less. Instead of being negative 9.8, it's only negative 6.5. As the air resistance continues to increase, and now the drag is 600 newtons, now the acceleration is negative 3.1 meters per second squared. So you can see there's not as much acceleration. Instead of adding 9.8 for every second that the person falls down, you're going to be adding 6.5 here. And then 3.1 here. So we're not really increasing speed that fast anymore. But note that the weight force is still greater than the drag force. So our gravity is still negative 882, but our drag, or our air resistance, is still only 600. So they're still uneven. But the drag is still increasing. So remember, we went from 0 to 300 to 600, and now our drag, or air resistance, is finally 882, which is the exact equal and opposite vector as our gravity vector, which is negative 882. So eventually the force of air resistance is equal and opposite to the force of gravity, and so the net force acting on the falling object is 0. So remember we talked about calculating net force. So you have a positive 882 and a negative 882. When you add these two forces together, you're going to get 0. So our net force is 0. Because these two forces are balanced. They're equal. They're equal and opposite, so they help to cancel each other out. So notice that because these forces are balanced, the net force is 0, right? We've talked about a net force being 0. If you don't have any net force acting on the object, there is no acceleration. So notice, at first we had an acceleration of negative 9.8, then it was negative 6.5, negative 3.1, and then finally 0. So the object is no longer accelerating. So whatever speed it's locked in at, maybe it's 23 meters per second, it's locked at that speed. It's no longer going to keep going 23, 24, 25. No, it's going to stop at 23 meters per second. And so the rest of that person's journey down to the ground, it's going to be traveling at 23 meters per second. It is locked in. There is no more acceleration. All right. So remember, terminal velocity is that ending velocity. It's that final velocity that gets locked in once the forces are balanced. So once our drag is balanced in with our gravity, then we have a net force of 0, we have no acceleration, and whatever that final velocity is, that is the velocity that the object has as it continues to fall. It's the maximum velocity. All right, thanks for watching.